Hello everyone, welcome to our 5th video lecture on social statistics, and for this video we'll talk about hypothesis testing. So we're going to review some related terms in relation to hypothesis testing, and then I'll walk you through the 4 steps of hypothesis testing. I'm going to be discussing with you the different types of the way you can articulate hypotheses. We're also going to be talking about type 1 and type 2 errors in relation to how you interpret findings from your hypothesis testing. And we're also going to be talking about normal distribution to be able to help you in terms later of identifying which statistical tests you have to use in order for you to test your hypothesis, and then also some tenets or some principles related to the difference of parametric and nonparametric tests. So, as explained earlier, we have 2 general types of strategies in doing statistics. We have the descriptive statistics and inferential statistics. Descriptive statistics, by its name, it means that we want to describe the data at hand. And we have learned that frequency, percentage, mean, median, mode, and then of course you have measures of variability, and later we'll learn about measures of shape. That is included in the discussion of describing your current data set. And the second type is inferential statistics, which we usually use when we try to address our hypothesis in a research project. So, inferential statistics involves techniques that use the obtained sample data to infer to the population. So, if you remember your basic statistics classes way back in your high school and in your general mathematics class, you know that when we try to infer something in the population because of posterity reasons, and of course we want to economize our resources, we don't really get the whole of the population, especially if the population is big. So when we talk about, for example, the whole of the Philippines or the whole of the university, it would be unwise or non-economical if we get them all. No? So if we do some form of sampling, which is of course a segment of the larger population to which we want to generalize our results to, then our ability to be able to approximate relationships among variables within a sample in order to infer to a larger population is called the inferential statistics. So, as we also explained earlier, the application of inferential statistics is in the area of hypothesis testing. So, this is kind of where we try to see whether or not certain variables are related to each other in order to help us explain and predict certain phenomena based on our assumed cause and effects or assumed predictors and outcomes. So, in quantitative research, you will be doing as one of the terminal activities or the terminal objectives of your research is hypothesis testing. So basically, it's a process that helps the researcher decide whether to accept or reject a formulated statement or hypothesis after the evaluation of a sample and draw inferences about the population of interest. So basically, when we try to start a research, we are attempting to explain a certain phenomenon, and in order to explain a certain phenomenon, we try to quantify that phenomenon by identifying certain measures in order for us to be able to explain that phenomenon. So for example, if you want to know whether or not, does stress predict low grades or does stress predict academic performance? So maybe we would like to quantify stress by asking the students to answer a stress scale, or maybe we would want to go for a more biological way of measuring stress, like for example vital signs. But usually for social statistics we just use scales or questionnaires. And then in order for us to approximate or measure academic performance, we can probably measure that using the grades of the students. And then what we do is in hypothesis testing is that we try to see whether or not this data are correlated, or are they related to each other, are they associated, and then that basically answers our question whether in this sample we can generalize in the rest of the population that really stress is contributory to academic performance, whether it's positive or negative. So basically, in most of the research in the undergraduate level, those are the terminal outcomes that you would want to achieve. No? So it's intended to help differentiate between real and random patterns of data. So because we want to see, for example, there's that large that belief that, for example, yun nga, stress decreases academic performance. But is it really, that theoretically has support? But we can't just take theory on face value. We have to test it. If you remember our scientific method, diba, we start with a question, and then we set our hypothesis, we observe, we make our experiments. In this case, in social research, we collect data and then we analyze them and see whether or not our theoretical assumptions hold water. And most of the time, our theoretical assumptions that hold our hypothesis will hold water or will be confirmed after statistical tests by the empirical data that we collect. Most of the time, people who are stressed would more likely have lesser academic scores or academic performance. But sometimes, like for example, I had a personal experience wherein we collected data for COVID-19 anxiety, and we wanted to see whether or not this was correlated with quality of life of students. So what we expected is that when you have worries in relation to COVID-19, you would have lesser levels of quality of life. But the empirical data that came with us was that there was a significant relationship, but the significant relationship was not negative, meaning that anxiety did not decrease quality of life, but it actually minimally increased quality of life. And that's the reason why we do research, because we want to always test the theories that we have, whether they would be eventually falsified by the new data that are coming in. There's so many theories that have been, thought of before that no longer hold water today because empirical data has continuously and repetitively did not support these theories. But of course, there are theories that have, of course, become a staple because up until now they're very relevant, they're still used, and they are still coming up with positive results. But some theories no longer. And that's the reason why we do research, and that's why we do statistical testing. That's why we always have to, to always create hypotheses and test the hypotheses that are based on theories, because we always want to check whether what is happening on the ground is really what is the current nature of what the theory is saying. Or do we have to ratify the theory or improve the theory? Do we want to contextualize the theory, etc., etc.? So we want to be able to differentiate real and random patterns of data. Okay? So real relationship between two variables or a simple random fluctuation that would be expected just by chance. So a real, if our hypothesis is founded, then there's an actual relationship between the variables. Or maybe this is just something that nagkataon lang, that was by chance that and by probability that this is the distribution of the values in the data set, but they don't really behave in a significant way that that variable A and variable B are correlated with each other. So that is what we are trying to test in hypothesis testing. So the first step of doing hypothesis testing is to basically state the hypothesis. And if you're doing this in the context of research, there are certain research questions, especially the terminal research questions, that basically would guide you in terms of what hypothesis you would have to state. So basically, a hypothesis is a prediction or an intelligent guess about the behavior of variables in an unknown population. A statement that cannot be accepted or as true unless otherwise proven. So that's the nature of science. We hypothesize and we just don't philosophize and say that this is true. We just don't take it as truth. We don't just use justification. We just don't do rationalism in order to say that it is true. But we have to really back that up with empirical data, and we really have to run statistical tests to see whether or not this is just a random behavior of variables within a data set, or this is actually something that is predicting or is influencing another variable. Now, there are two general types of hypothesis that is tested when you go from one department and one university to the next. The way the type of hypothesis that they use is different. No, they may be different. No, but basically we have null hypothesis and alternative hypothesis. I'll just breeze through this because I know that you've had this in your more elementary statistics classes. So alternative hypothesis is usually represented by H sub A or H sub 1, and it is a statement that claims the variability of the dependent variable and its relation to the independent variable. So basically, when we do hypothesis testing, we're just saying whether or not variable A's variation is co-variating with another variable. And we'll discuss about different relationships in the next video. So there are two subtypes of alternative hypothesis or research hypothesis, and it could be non-directional. So an example of the way we would articulate a non-directional, a two-tailed or a non-directional alternative hypothesis would be academic stress has a significant relationship with academic performance. But it can also be one-tailed, meaning we are already assuming that there's a direction in the relationship. So for example, we can state it as academic stress has a negative relationship with academic performance. So when we say a negative relationship, it means that when variable A is high, variable B will be low, and vice versa. Another way of articulating that alternative hypothesis would be students who have higher anxiety or who have higher academic stress scores would more likely have lower academic performance. That's another way of stating an alternative directional hypothesis. All right, and then when we say that two variables have a positive relationship, when variable A is high, variable B will also be high, and vice versa. So an example of a theoretically positive relationship between variables would be, let's say, when a person has high level of social support, then the person would most likely have higher levels of mental well-being, and vice versa. So that's an example of a positive relationship. So we can assume that high levels that social support is positively correlated with mental well-being. And then we also have null hypothesis or statistical hypothesis, or H0. So it is a logical counterpart of the alternative hypothesis known as the no difference or no relationship hypothesis. It basically is a hypothesis that implies neutrality and objectivity, a hypothesis that negates the existence of something, and it usually begins with the phrase "there is no." And we in statistical testing or hypothesis testing, we first evaluate the null before we evaluate the directional alternative hypothesis. If the null is false, then the alternative must be true, right? So it's either in order for us to say that whether a variable A and variable B have a significant correlation, then we have to reject the null hypothesis first. And then if we do not reject the null hypothesis, that's the time we test the alternative hypothesis and see whether there is a direction, or what type of direction of the relationship does variable A and variable B have. So that's for your hypothesis, for your null hypothesis. So an example of how we articulate null hypothesis is there is no significant relationship between academic stress and academic performance. Another would be there is no significant relationship between social support and mental well-being. So as I said, when we do this in the context of a thesis or a dissertation, we usually look at the more terminal research questions in our statement of the problem. So an example probably of a statement of the problem that we would like to kind of articulate as a hypothesis would be, let's say, there is a significant relationship between national resilience and life satisfaction. Is there a significant relationship between national resilience and life satisfaction? So if we're going to articulate this as a null hypothesis, then I would do it this way. There is no significant relationship between national resilience and life satisfaction. Note here that we began with the phrase there is no. And then for alternative hypothesis, national resilience is positively correlated with life satisfaction. So this is an example of a directional hypothesis, right? So that's national resilience is positively correlated with life satisfaction, or higher levels of life satisfaction would be observed among those who have higher levels of national resilience. So pagka mas mataas ang perception nila ng national resilience, mas mataas ang satisfaction nila sa kanilang buhay. And I think that's theoretically plausible. If we want to set this as a non-directional alternative hypothesis, I would articulate it as there is a significant relationship between national resilience and life satisfaction. Alright? So that is for your step 1, articulating or stating the hypothesis. Next is setting the criteria or decision that would say that we would reject the null hypothesis, right? Or we do not or fail to reject the null hypothesis. So we set the alpha level or level of significance, the alpha level. And basically, this is what we look at. The first thing that we look at after the statistical software has generated the results, ito yung usually nating first na tinitingnan to say whether or not there is enough evidence for us to reject an hypothesis and infer that there's a significant relationship between variable A and variable B. So we always evaluate the results of an experiment or a non-experimental research by assessing the null hypothesis, because we can calculate the set probability of chance events. So, and usually we set it at the beginning of the study. So usually our researchers set it as 0.05, meaning that there's only that there is a 5% chance that the relationship that we're looking at is happening by chance. And then of course we have 0.01, there is a 1% chance that what we're looking at, or the relationship that we are seeing as a behavior of the variables in the data set, is happening by chance and not really a significant relationship. Now, in the social sciences, in the behavioral sciences, we usually set it at 0.05. Even actually in other types of sciences. But in more like life and death situations, we usually use 0.01. Like in medical research, in drug research, we use 0.01 because so that it would decrease the number of chances for us to say that, a certain drug A is, really effective or not. But again, like I said, this is what we use, 0.05. So it's like automatic. It's an automatic value that we already choose. And we set this up, when we report our methodology section. This is a part of our data analysis procedure. Next is, of course, now that we have set the hypothesis, then we have to run the research, collect the data, and compute the statistics. And we're going to be doing that later in the future, based on what type of question you're asking. So the statistical tool you will use to compute the statistics and the alpha level or p-value will be based on the nature of the variables that you will be working with, as I explained earlier. And this is going to be the content of our future lectures. For example, if my variable A is dichotomous, just like, for example, a sex assigned at birth, and my outcome variable or my dependent variable is a continuous variable, like, for example, depression scores, what type of test will I be using? Or if my variable A is a continuous variable, like, for example, let's say a household size, right? A continuous variable, and then our outcome variable is, let's say, monthly savings of the household in pesos, right? So that's another continuous variable. In order for us to test the relationship between these two variables, the test that we will use for my first example on the sex assigned at birth and the other one that I just said would be different. And that would be what we will be discussing in the next video lectures. And then finally, make a decision. So now you compare the resultant p-value with the p-value that you've set in the beginning, with the criteria that you've set in the beginning. So if it's lower than 0.05, because that's what we want to see. If it's lower than 0.05, then it is a significant relationship, or we reject there's enough evidence for us to be rejecting the null hypothesis. No? So we make that decision, and we based on the criteria. Now, the question now is, when we decide that we have to reject the null hypothesis and, let's say, accept or push through with our alternative hypothesis and really report in our paper that, yes, we have a significant finding, how sure are we that that's true? Because remember that in statistics, this is really a game of chance. And we can only really approximate using the data that we are holding and the sample that we've collected data from based on what we have. And we're just generalizing into the population. And I guess that's one of the reasons why we have these conversations in relation to whether or not the pre-electoral survey results are true or not. Because we want to see, can we trust, the data that we're seeing here, right? So if our paper says that yes, there's a significant difference, or if a paper is shown to you and they say that there is a significant difference or there's a significant relationship between variable A and variable B, how do we as readers consume that? Do we just readily take it? And a lot of the answers to that question is really based on how the study was designed. Of course, there are so many issues in terms of objectivity of the design, the reliability of how the design of the research was created. But also, we can infer some things in relation to how hypothesis testing was really set up prior to the collection of the data and the application of the statistical strategy that was used. So there are two types of error that we kind of look at if we try to evaluate whether or not this is something that we take as really significant or not significant. So, or when we are presented with someone saying this is significant. So type 1 error is defined as a decision to reject the null hypothesis. Well, in fact, in reality, it's actually true. And usually we protect ourselves from saying that we reject the null hypothesis when in fact it's the null hypothesis is true, is setting up the significance level. So the better the significance level, so the lesser the critical area is lesser, the better, of course, because the lesser the chances for us to say that this is only happening by chance. So that's type 1 error. If we rejected the null hypothesis, but in reality, it's really true, then that's type 1 error. And then type 2 error is that we suggest that there is no significant relationship, but in reality, there is a significant relationship. So we were not able to we interpreted it wrong. So that's called the type 2 error. Of course, what we would want to achieve is that when we interpret our findings as retain or not reject the null hypothesis, we really hope that, in this case, sana totoo nga na siya ay in reality, talagang totoo siya na null hypothesis is true. So that is what we want to see. In short, what we want to have is that the interpretation should be parallel of what's really happening in reality. Of course, the reality, it's hard to really approximate that. It's hard to know. That's why we're collecting the data. But we really have to take in measures in order for us to be able to really interpret our findings based on what's really happening in reality. So as I explained, in type 1 error, the way we protect ourselves from getting type 1 error is setting up a significance level and interpreting within the significance level. So we don't say that there is a significant relationship when it is higher or equal to 0.05, the p-value. So that's the rule here. Now, type 2 error is a little bit trickier and needs more needs more effort from the researcher. Kasi for example, you need to set a statistical power. So what is a statistical power? So statistical power protects us from type 2 error. The type 2 error, as I explained earlier, is the failure to reject a false null hypothesis. But in reality, the independent variable really has an influence on the dependent variable. But the hypothesis testing that we did failed to discover it. And what are the, how do we make sure that we won't be able to commit that error? And this is setting up a good statistical power. So the power of a statistical test is the probability that the test will correctly reject it if it's an actual false null hypothesis. The probability that the test will correctly detect a real effect between the independent variable and the dependent variable. So that's statistical power. So usually the acceptable statistical power when we, compute things is around 0.8. That's the acceptable statistical power. And then we have, of course, getting enough sample size to increase or to decrease chances of getting type 2 error. That's the reason why I am not happy with just, 100 participants for our survey. We wanted to really, blow up the number of people because we want to veer away from type 2 error as much as possible. So you will also be encountering other elements of hypothesis testing when the statistics are going to be taught to you. So you will be learning about different test statistics. Like for example, for t-test, you will be exposed to t statistics. If it's Mann-Whitney U, that's a u statistic. If it's chi-squared, that's an x-squared statistic. So it would be different from one test to another, but I will not be discussing that today because we have to have like a focused explanation for each statistical test based on the type of relationship that we want to uncover. And then, of course, there's also a standardized or an estimation of the error within the test statistics, although we don't really interpret that, but we sometimes have to report that. And then we also have effect sizes because there may be a significant effect, but the effect size will tell us whether or not that significant effect is substantial or it's only a small type of effect. And the effect size is usually differing from one test to the next. So the way we would interpret the effect size in independent t-test would be different from a Pearson R, would be different from a multiple regression test. And again, we will focus that in our future videos later. And then, of course, we have the alpha level. I've discussed this earlier, or the p-value that we set in the beginning. And if our statistical test would yield a value that's lesser than 0.05 in social and behavioral statistics, then yes, there is enough evidence for us to reject the null hypothesis and establish that there is a significant relationship or suggest that there is a significant relationship. And then we just earlier discussed statistical power. In order for us to see whether or not we have the enough sample size to be able to protect ourselves from type 2 error. Now, there are two sets of inferential statistics that you will encounter and that you will have to use based on the nature of the variable and the nature of the distribution of your data set. And there are two types. You have the parametric and the nonparametric test. Before I go to defining parametric and nonparametric test, we have to identify the more important criteria for us to choose a parametric test. So in order for us to choose a parametric test, the continuous variables in our hypothesis must be normally distributed. So yun ang isa sa pinaka-importante. Kailangan normally distributed siya. Sometimes, more conservative researchers would say that we can only assume normal distribution when the participants or the respondents are collected randomly or are recruited randomly And then the more liberal or more progressive researchers and statisticians would say, you just have to have enough sample size with a good statistical power and you're good to go. You can do parametric statistics. But there are ways for us, aside from the amount of sample that we have and the way the sample was recruited, it can give us clues whether or not a certain variable is normally distributed in a given sample. And of course, normality, and you have heard of this probably in your elementary statistics, a normally distributed data will, when you set that in a histogram, you will be able to come up with a normal curve. And if we're able to assume, if you're able to have a normal curve, then that's parametric. But again, it's more than just, I can see that is a bell-shaped symmetrical curve. Then I can use a parametric tests. There are tests that we can use in order for us to really ascertain that the distribution of a certain variable in your study is symmetrical. And remember, this is for continuous variables. So first we can employ measures of shape. So we have skewness and kurtosis. So skewness is kind of looking at the whole thing horizontally. So it's looking at the symmetry of the distribution. So one of the things that we have to look at when we want to assume a normal distribution is hopefully it's a unimodal distribution. So just like this, unimodal. Ayan, isa lang yung peak niya. There's only one mode. And then of course, we have multimodal or bimodal. Pag bimodal, you would see here na dalawa yung mode niya. And then we also have multimodal. Ibig sabihin, it has many peaks. Now, when a certain variable has multiple modes, we can kind of suspect that maybe there is another variable at work here that may be creating these new peaks, and probably inferential statistics will be able to help us in trying to see whether or not we're looking at just one distribution with two modes, or we're looking at two distributions and it just so happens that they're together in a sample. And then when we talk about another skewness, again, there are three ways that we three characteristics or three levels of skewness. We have symmetric, which is the most ideal. So it has, pantay yung left and the right side. And then it can be skewed to the left, meaning they're more it's more negatively skewed, or it can be skewed to the right, or it's more positively skewed. So when we run our skewness tests, if it's less than 1, then it's highly, or greater than 1, then it's highly skewed. Of course, the negative and the positive will tell you whether it's highly positively or highly negatively skewed. And then if it's between -1 and less than 0.5, positive or negative, then it's moderately skewed. And then if it's less than plus minus 0.5, then it's approximately symmetric. So in order for us to say that, that it is really assuming a bell curve, then we would hope that it's less than 0.5 for us to say that the distribution of a given continuous variable in your population or in your sample is actually symmetrically skewed. The next measure of shape, in order for us to actually identify whether or not a certain continuous variable is normally distributed in your population, is kurtosis. So kurtosis is looking at it at a vertical level, So that's the sharpness of the peak of the frequency distribution curve. So if it's not too sharp, then it's curtic. If it's very sharp, then that's leptokurtic, as seen here. And then we have platykurtic, where it's more flat, So just like very similar to how we interpret skewness, if it's greater than +1, then the distribution is too peak. If it's less than -1, the distribution is too flat. And and then the closer it is to 0, the better, the more mesocortic it is. And of course, we want we want a normal distribution to be symmetrically skewed and also mesocortic in nature, or normal lang kanyang kurtosis. But usually, researchers don't really have to go through the skewness and the kurtosis anymore. They can just go for a more direct measurement of normality, and that is Shapiro-Wilk test, no, which usually we immediately test in the beginning so that we know whether or not we're going to use parametric or non-parametric tests. So the Shapiro-Wilk test, which was proposed by Shapiro and Wilk in 1965, calculates a W statistic that tests whether a random sample comes from a normal distribution. So if the p-value is less than or equal to 0.05, then ibig sabihin, it is not normal. So if it's not normal, then there is, we should approach this as a, non-parametric sample, no? Or we should use non-parametric tests for this sample. So again, for every type of hypothesis or relationships that we're trying to test, there is a parametric variant and a non-parametric variant. Now, there's again, one of the main conditions that we want to see if we want to use a parametric is that it has to be normally distributed. If hindi siya normally distributed, no, for example, the Shapiro-Wilk test is significant, less than 0.05, or it's the kurtosis and the skewness is not okay, then maybe we should use a non-parametric test. And then the variance, no, among the variables is homogeneous. For parametric, for non-parametric, it can be any, no? So in short, if the criteria for parametric is not met, then we use non-parametric. And then the typical outcome variable that we look at for parametric are ratio and interval, or in continuous variables. If the outcome variable is ordinal or nominal, we usually use non-parametric. And then for the dataset relationships, we want them to be independent. For non-parametric, it can be any dataset relationships. For the central measure that we use for parametric, it's mean. In non-parametric, we still use mean. No, we actually don't report the median, but according to statisticians, no, we really have to also report the median. But again, for our practices, no, we just usually do the mean, especially because these are continuous variables. And then, why do we want to achieve parametric? So, di ba, ang dami ng mga requirements ng parametric. Di ba, nawag non-parametric na lang tayo. It's just that parametric tests are more robust, no, and they can draw more conclusions, draw more insights, can give us better, a more dramatic way of interpreting the data compared to non-parametric tests, no. But most often than not, especially if in our department in the in sociology and behavioral sciences, we're quite conservative, no. If randomization of participants were not achieved and normal distribution is really apparently not achieved, we really have to do non-parametric tests. But again, there are more liberal researchers and statisticians who would really say that, who would accept that once there's a large enough sample size, and we can probably go for parametric tests and then just do statistical corrections later. The statistical corrections, we will not be covering that in our whole course because that's a little bit more advanced. No? Examples of corrections for us to be able to rationalize or justify the use of parametric test would be probably statistical controls or bootstrapping. But again, those are not a part of our syllabus. And, so usually just go for non-parametric. Again, the danger for non-parametric is that they're not as conclusive as we'd like them to be compared to a parametric test. So that's introduction to hypothesis testing. We will do actual hypothesis testing later. We will just have to go from one type of inferential statistic to the next. All right? So thank you so much. Hi, okay, so in this part, I'm going to be demonstrating to you how to run some tests that will be able to kind of give us an approximation whether or not our continuous variables in a data set
are normally distributed. All right. So I am loading here the sample data set that we collected in national resilience and life satisfaction. So we're going to look at national resilience and life satisfaction and basically ask the question, um, are the different domains of national resilience and the singular domain of life satisfaction, are they normally distributed, and therefore can we make use of parametric tests, again, if we are coming in as more conservative types of researchers or statisticians? All right, so the CSV is already loaded here, so um, let's try now to run. All right, so go to analysis and then just it's in under descriptives. All right, so I would do the usuals, no, make this rows, remove this things that we don't need yet, no. So what we want are the three different we have the three we have the IWMC, SSJ, and TPI, and then we also have the LSS, SWLS here. So we'll place it under our variables here because these are the continuous variables that we want to see um, whether they're normally distributed or not. No, so let's do first the measures of shape. So based on my earlier discussion, we have skewness and kurtosis. So let's do skewness first. No? But before that, sorry, before I test for the values of skewness, let's try to visualize first. No? So there are actually visualizing tools that can kind of help us approximate and kind of eyeball the normal distribution. And what I usually use is the histogram. So of course, you have been introduced to the histogram earlier, in the data visualization. You can actually do this via Jamovi. So for example, I click histogram and there you go. So it gives us an information, a visual information of the means per domains of national resilience and also in the SWLS. And when you look at SWLS, it appears like there are multiple modes because there are different peaks as I see it here, no? But again, it could mean anything. No, there could be other variables in the set that we might not be controlling. Again, by the way, I wasn't able to include that in the discussion earlier. That another way that type 1 error can come is not only in terms of setting the significance level, but also being able to control for confounders. Confounders are other things or other variables that are not included in your study that might influence the behavior of the variables in your study. So if you're not able to control them statistically, or at least from the vantage point of recruitment, then that could be a problem for you. But anyway, here is your your histograms, not Instagram, histograms. No, so, and then we can probably actually like visualize the curves by clicking density here, right? So ayan, it gives us a more. So when you look at the data, it appears like some, at least for purposes of like eyeballing it, some of them are visually skewed. Like this one appears to be visually skewed, positively visually skewed. This one is a little bit more symmetrical in terms of skewness. You could see it here. This one is really positively skewed, and this one, I think this one is a little bit more symmetrical, but we have issues in relation to modes. But again, we have calculations for us to be able to do, for us to interpret skewness later. We can also do box plots, and the box plot will also be helpful in telling us whether there are outliers. And you have learned box plots before. And you see here, we have some outliers for this domain. This one, I think this SSJ is, I think this means social justice. No, this appears to be a little bit more normally distributed compared to the other continuous variables that we are looking at here. This one really positively skewed. This is trust in public institutions, so it's kind of skewed towards lower scores. This one is a little bit more symmetrical, right? Um, Ayan. So those are your the way you can visualize. But of course, in order for you to really confirm, mathematically whether there is really non-symmetry in terms of skewness, you can click skewness here, and you can see again, when you look at skewness, it has to be less than, if it's more than one, then there's a problem in relation to that. If it's more than 0.5, then, so as you can see here, TPI is more than 0.5. So it's a little bit moderately skewed, no? The rest are not skewed. No? So si TPI lang talaga yung moderately skewed, positively skewed, no? And this is the standard error, okay? And then we have kurtosis. So for kurtosis, again, we're looking at the vertical, the peak. And as you can see here, all of them are less than 1. All of them are negative. So they're a little bit platycortic. Leptocortic, yeah. So let me check again if I am interpreting it correctly, because I don't want to wait. So I'm correct. So the negative ones means that it is a little bit platycortic, but there's not much issues because it's not greater than or less than 1. I mean, not positive or negative 1. So the kurtosis is fine, no. But we have issues more on skewness. But like I said, no, we can go directly to the measure of normality. Here we have Shapiro-Wilk. And what we look at is the p-value. And if the p-value is less than 0.05, then it means that it's not normal. So what we want to see here is that it should be it's more than 0.05. And as you can see, it's less than 0.001. So we can assume that all of the continuous variables that we have collected are not normal. And therefore, a more conservative way of approaching this in our hypothesis later is to use non-parametric tests. Or you can probably use parametric tests but do statistical corrections like bootstrapping later. But yeah. And this is one of the things that you can probably see for really and then again, one of the contributory mechanisms here is you have a little bit of outliers, as you can see in your box plot diagrams. And then another would be, of course, that we just collected convenient sampling, no? If it's a little bit more random, if our recruitment was more random, then we would expect more, then we would expect a little bit more normal distribution. But this is what we have, and this is the data that we're currently holding, and we will make do of what we have at the moment, no? What I want you to do is for your variables, for the main continuous variables, the first one being citizenship, and the second one is the well-being variable that is with you. I want you to run. I want you to create. I want you to first look at the hypotheses that have you have to articulate hypothesis, null and alternative hypothesis based on the approved research questions that are inferential in your study. Number 2 is to visualize the continuous variables in your study using a histogram, density, and box plot, and then describe, what you see or what you eyeball. And then you have your skewness. You have to do your measure the skewness for each domain of the variables, measure the kurtosis, compute for the Shapiro-Wilk, and then appraise, what can you say about the skewness, what can you say about the kurtosis, and what can you say about the overall normality based on the Shapiro-Wilk test. So that would be your group assignment. All right.